right to his ass.
Okay, so now that we've talked about the phase diagrams and a little bit about phase change, we need to talk about it at the molecular level a little bit better. So for this example, we're going to talk about water, and we're going to talk not about boiling, but about evaporation, what's actually happening more passively at various temperatures. So to do that, we need to kind of look at what the environment is like for an individual water molecule in a couple of different ways. When water molecules are down in the liquid, they're held together by a large network of hydrogen bonds that's three-dimensional, so you get a very, very coherent liquid, and therefore it's a liquid despite having a very relatively small molecular weight. If we look at a molecule that's exactly at the surface, on the other hand, what we see is that it does not have interactions in all three dimensions anymore. And that kind of brings us to this.
I want to get away. I want to fly away. Yeah.
Finally, since at any point those intermolecular forces, the hydrogen bonds, are on and off, they're being switched on and off between different molecules at any given moment, some of those molecules at the surface are actually going to have an instant where they're not really attracted to anything, and at that point they can escape. Because by the time that switch off happens again, they're already floating away. And the important point about that, in the words of the late Glenn Fry,
"'Cause I'm already gone. Yes, I'm already gone."
which we talked about originally when we talked about the gases and real gas laws, was that essentially the gas phase, behaving ideally, which is most of the time, has essentially no attraction between the molecules. There's no interaction between them, and here's why that is. In the liquid phase, 1 mole of water takes up roughly 18 milliliters, give or take slight variations in density based on temperature. If we look at STP for the gas, on the other hand, we're talking about 22.4 liters. We're talking about a 1,000-fold expansion in volume. These things are very far apart compared to the liquid or solid phase, and there is no more attraction anymore. So the second they get a chance to run free, that's exactly what they're going to do. Now, as we go to talk about this, we're going to have to revise some of our terminology a little bit, and a little bit of this was in the phase diagrams discussion, but we need to talk about it in a little bit more detail. The first is the definition of the word boiling point. It's a bit of a misnomer, but it's an important concept regardless, and what it technically means is the point where the partial pressure of the gas, which we're going to refer to as the vapor pressure at this point, becomes equal to atmospheric pressure. Just to refresh your memory on a few things, partial pressure is a function of the mole fraction, x of A, times the total pressure of gas around the system. The mole fraction is the number of moles of A as a gas out of the total number of moles of gas in the system, and of course the ideal gas law, PV equals nRT. We're not really going to work with that specifically, but just to give us proportion with relative to temperature, it's good to remind you of it. Now, to be a little bit more specific, vapor pressure is not just a synonym for partial pressure. It's a specific condition of partial pressure. It is the partial pressure of a gas over a sample of that liquid. So very much like the escaping water molecules I showed over the liquid in the first couple of drawings, that's what we're talking about here, is the gas that's over a sample of the liquid. The critical relationship in understanding all of this is something called the Clausius-Clapeyron equation, and it relates pressure, the enthalpy of vaporization, and the temperature. I show you the original proportion here, not really useful in a one data point version, but if we look at it as a 2-point version, we can actually cancel out any constants and get an equation. So we have a natural log relationship between the pressure ratios, an inverted temperature relationship, and the enthalpy of vaporization. R here is the energy form of the gas constant that is always going to be a given. So let's have a look what that looks like in practical and, more importantly, problem-solving terms. It would look something like this. Given the day that I actually recorded this, it was 5 degrees C outside. I want some idea of what the pressure of water in the atmosphere is, so that's the question. We dig out our Clausius-Clapeyron equation again, And there's a question here because I have one temperature value and nothing else. The heat of vaporization for common liquids can be looked up in tables, so that's not a terrible thing, as well as the gas constant would be given in its energy form. But still, we have 4 variables and we're only given a data point for one of them, 5 degrees C, as one of the temperatures. I have nothing pressure-wise here. Did I forget something? And the answer is no, I didn't. First, before we start talking about data points, let's talk about units, because this is a place where more than one person will blow this type of question. Not keeping the units straight. When I was a student taking my first chemistry course, my chemistry professor had a rule that any units left off were worth -5. Even if the question was only worth 2 points, he would still take off 5 points. You could get negative scores on your exams because it's that important. If you start using the wrong units, they don't cancel, they don't make any sense, you start getting sign changes, you start getting division by 0, you get all kinds of weird things that should never happen if you keep the units straight. So, unit problem number 1. Enthalpy terms are usually in kilojoule terms. The R gas constant is not. It's in joules. Those two don't match. You have to fix that before you can do anything else. Okay, so far so good, as long as you can remember how to divide by 1,000. Not a big deal. Step number 2, temperature. Oh, look at that. The R, the gas constant, has a Kelvin unit. I gave you a temperature, and reality gives you a temperature, if you're just pulling it out of the weather like I did for this question, that is not in Kelvin degrees. You have to put it there. So you're usually given temperatures in Celsius from observational data. You're going to have to put that yourself into Kelvin. So that is a difference of 273, 273.15 to be more precise, but we'll take 273 as a round number. So we're looking at 278 Kelvin for 5 degrees C. Now, we still don't have any extra data points, but we've got our units right, so that's a start. Now we can start thinking about data. What am I missing here? I can solve for the pressure. The question asked me to solve for the pressure at that temperature, but I have to have another data point. I have to have a P1 and a T1 if I'm going to use that 278 Kelvin as T2 to solve for the pressure at point number 2. So what is that going to be? That definition we talked about. Boiling point. The boiling point for a liquid is the point where its partial pressure becomes equal to atmospheric pressure, or its vapor pressure becomes equal to atmospheric pressure. Well, we happen to know what the boiling point of water is. It's 100 degrees C. And we happen to know what standard atmospheric pressure is 1 atmosphere or 760 millimeters of mercury. So we have a data point from the boiling point data. For most common liquids, we could look that up. So we have a data point, if we don't happen to know it off the top of our head, which you should know for water. But if we don't know it off the top of our head, we can look up the temperature, and that will give us one of our points because the boiling point temperature is 1 atmosphere of pressure. So we know actually one of our data points. We still have to be careful with the units. We don't want to screw that up with the temperature here at 100 degrees C. Has to be in Kelvin. So now every unit matches. I now have 2 temperatures, 1 pressure, the heat of vaporization, and the R. The only variable left in the equation is P2. I'm good to go. I can solve a 1 variable equation, no problem. So here's what that looks like. We start putting the numbers in place. Now, something I'm going to mention here, and you'll notice this with other videos as I post them, I tend to go very, very stepwise through the numbers. That's not trying to insult anyone's intelligence. I'm not trying to bore you to death. I'm trying to get you to pay attention. I expect you're going to do the problem and then come back and look at this answer. But the point is, I'm going to try and point out places where a lot of people over the years have made relatively silly math problem errors. It's bad to not do well in a course because you don't understand it. It's worse to do poorly in a course when you did understand it, but the math tripped you up or your calculator tripped you up. We'd like to avoid that. So part of why I go through things a little bit more slowly in this is so you can see what I did and so you can hopefully avoid the same types of mistakes that many, many students over the years have made. You got a couple of different problems here that people will make errors in mathematically. One, you have a natural log relationship. That tends to screw people up. Not saying that that makes anybody, less intelligent. It's just something that commonly is a mistake. The other is the inverted temperatures. If you don't invert these correctly, you will never get this to work. Practice this until you get the exact same answers that I have written down in this question. All right, so when I do it, here's what we get. The inverted temperatures subtracted from each other gives me a negative number, but it's a very tiny negative number. I still have my natural log relationship for the moment. I haven't gotten rid of that yet. I multiply that through by the delta H VAP over R, and I get roughly negative 4.5. Okay, well, does that make any sense? Yes, it does. We're dropping the temperature. We know that pressure and temperature are proportional for a gas, so if I drop the temperature, I expect from 100 degrees C, the boiling point where I've got 1 atmosphere of pressure, if I drop that temperature by almost 100 degrees, then I expect that the pressure is going to drop pretty drastically, which means I'm going to have a relatively small fraction inside of that natural log. A natural log of a number less than 1 is going to have a negative answer to it. So as you're going through this, you can keep some degree of logic in it without knowing the right answer, but knowing about how the signs are going to go so that you can see if something went wrong when you were there. All right, so I know I've got a negative number. It may be a relatively large negative number, probably not that large, but still. So if I take this the rest of the way through, here's the other math problem, and that is getting rid of that natural log. To get rid of a natural log, you have to raise both sides to the e power. Oh my goodness, this is a creative thing. I've seen people do the most bizarre things here, from ignoring the fact that it's natural log and using 10 to the x, to natural logging one side and not the other. I've seen people do some very bizarre things here. So you have a natural log button. The inverse that's usually written right above that on your calculator says e to the x. There's a reason for that. That is the inverse function. So if I want to get rid of it on one side, I have to invert the function on both sides. I raise both to the power of e as exponents of e. So on one side, I have nothing left. E and natural log cancel each other out. I get P2 over 760. On the other side, I get e raised to that minus roughly 4.5. And that's going to give me an answer, which is going to give me a relatively small final pressure. Does that make sense? Yes, it does, because we're talking about a drastic drop in temperature. There's not a lot of water vapor over a sample of very cold water. Those molecules at the surface from the start of the lecture need the energy to escape with. If we keep dropping the temperature, there's not that much energy around to play with, so not as many of them can get away from the surface. It takes energy to jump and break away from the rest of the pack. So we're talking about a pressure that's roughly 1% of atmospheric pressure, a little bit more, but the point is, it's a very tiny pressure. Okay, so we see all the time, you can go to the phone, look at your weather app, and it's going to give you the humidity outside at any given point. It's not going to give you anything in pressure terms. Now, I looked up the data for this right as I was actually writing all this out. What I get is I get a percent humidity. And what does that mean? Percentage of what? Well, here's the trick. Remember what vapor pressure is. Vapor pressure is the pressure of a gas over a sample of the liquid. Most of us, this time of year at least, when we're checking the weather, are not thinking about being over the liquid while we do it. We're not out on the ocean on a boat or something. We're over land. Land is not a sample of liquid water. So the vapor pressure over the ocean has no real relevance here. It does have relevance because of air circulation, but it's not a direct relationship. So what we get is a percentage given to us of how much moisture is in the air at a weather station, and that's used as a percentage of how much would be in the air under the same conditions over liquid water, so presumably over the ocean. So here's what we're given on a given day. We're given that this day was 38% humidity, and specifically they say relative humidity, relative to the maximum amount possible at that temperature, which is what we calculated earlier. And we're given atmospheric pressure in inches, which you can convert to millimeters of mercury, a little above 1 atmosphere today. 760 is 1 atmosphere. It's 769.9. Okay, so slightly variations on our calculations, but the point is we have a relatively low humidity compared to what's supposed to be in the air if I were standing over a lake or the ocean. The ocean with ions in it's a little different. With one of a pure sample of water. Okay, well, what does that mean? It means that the air does not have the maximum amount of water in it for the temperature. What's the consequence of that? Everyone knows it, this time of year especially, is that the air is so-called dry. What that means is that as just you're breathing, it dries out your nasal passages. So you get, feeling like there's concrete in your nose and your sinuses. Your body tries to compensate for that by overproducing your sinus and nasal and throat lubricant. So what you get this time of year, runny noses, post-nasal drip, all the time. Most people this time of year are blowing their nose every half an hour or so because, if you're outside anyway, because the air is forcing your system to overcompensate because the air is too dry. Now, that is a practical application of this, a relatively unpleasant one, but it is one that you see and that you can at least experience to some extent, and you can even see this data come up in the Weather Channel app or whatever weather app you use, and now you know what relative humidity actually means. It's relative to what should be there as a maximum if we're in a place where we're over water. Why is it not that maximum? Well, let's say that the air is blowing directly west, and we're getting air from directly over the ocean. It isn't, but let's presume we are. Well, as you go over land, as the altitude changes, the airflow has to go up, and that air changes temperature, and so moisture drops out. So that by the time you get significantly inland, the moisture content has changed quite a bit because of temperature and altitude changes. So that you don't have that maximum amount of water in it anymore. And as I said, this is data from my town, which is about an hour from the ocean by air, well, about 60 miles from the ocean by air, and you can see that the theoretical humidity has dropped off by about 60% since the air left the ocean. Now, realistically, that's not the direction the airflow is coming into us, but it's a simplified example. There's a lot more land that the air that is coming down to us from northwest has to go over, and so a lot less moisture is there as it comes to us. All right, so last point here is comparing boiling point versus the enthalpy of vaporization. We would expect to see that these follow the same trend because basically they're talking about the same problem. That is the energy required to completely dissociate all of the intermolecular forces, converting a liquid into a gas. The enthalpy is the energy required to do that. The boiling point, of course, is the temperature where it happens. So we would expect to see that these are a relatively easy trend. We would also expect to tie it to what we've talked about already, that it flows pretty nicely with what we know about intermolecular forces. Okay, so let's look at that. This is a table of a few different liquids and gases, and you might expect that things that don't have really significant intermolecular forces, like argon gas, no bonds, so doesn't even have the simple London dispersion forces to deal with, very, very low boiling point, very low enthalpy of vaporization. Methane, natural gas, CH4, the last one on the list here, does have van der Waals forces, but that's all it's got, which is still relatively weak. I mean, it's still very weak comparatively. And so, again, what you're seeing, there's only a few of them, there's only 4 bonds, is a very low enthalpy of vaporization and a very low boiling point. Remember, this is 170 degrees, that's minus 170 degrees C, that boiling point, or minus 162 degrees C. So you're talking about really cold before that's going to become a liquid. What you don't see is a perfect correlation. So the first 3 examples are all examples where there's hydrogen bonding, water, ammonia at the top, and ethanol in the middle, and you don't see a perfect correlation. There are other factors involved here, something called entropy that we haven't talked about yet. We will near the end of the course, but the point is it should roughly follow. So what you see is going from a relatively low boiling point for ammonia compared to water. You see that going to water, the enthalpy jumps up considerably, and as does the boiling point. You're seeing for ethanol a comparable boiling point, so not exactly there. It boils about 75 degrees C, 80 degrees C, but the enthalpy is actually a little higher. As it turns out, the enthalpy of vaporization for water that I have written there is actually the value for 100 degrees C. The others are all standard values that are enthalpy of formation. If we look at the standard value, meaning 25 degrees C, the one for water is actually 44 and change, so it's actually slightly higher than ethanol. So normally delta H does not change drastically with temperature, but that one does change by about 8 or 9% over the range from 25 C to up to 100 C. So sometimes the trends will be slightly misleading, but they should follow the bulk idea that something with more intermolecular forces will have a higher boiling point and a higher enthalpy of vaporization, and the opposite is also true. Something with no or very little intermolecular forces will have a very low boiling point and a very low enthalpy of formation, and that's what you see here. So this is the basics of phase change in liquids to gases. Next topic, we're going to talk about what happens if we're not talking about a pure substance, but if we're talking about a mixture, and specifically if we're talking about solutions. This falls under the general category of colligative properties or solutions. That's the next chapter, the next topic.